Hello and welcome back to our interpolation video. In the last lecture, we talked about polynomial interpolation, which meant that we were able to find a line, a quadratic, or a higher order polynomial that went exactly through a certain number of data points. In this video, we're going to be talking about B-spline interpolation. So what does B-spline mean? Well, the B stands for basis function, and the basis function that we're going to be looking at looks like the following. So it's B equals the max of 1 minus x to the h, or divided by h, 0. And so if you plot this, it's a pyramid-like function that goes from minus h to h and 1. So that's what b to the x looks like, where h is our step size. Okay. So a lot of times we're going to need to deal with not just this basis function, but a shifted version of the basis function. So it's helpful to see what that looks like. So if our basis function is shifted by amount same as the step size, looks something like this. So it's centered on h and goes out to 2h. Okay. And so that's what the basis function looks like. And we're going to be able to look at it when we do interpolation. We're going to be finding a combination of these basis functions that goes exactly through the data. And so we're going to be finding a piecewise linear function. Okay. And so graphically, I'll show you down here at the bottom. If you have a x1, x2, and x3, then there's going to be a basis and points y1, y2, and y3. Then we're looking at a sum of basis functions that will end up connecting exactly through our data points. So it's a piecewise linear function, and it's actually summing. If I show you what the individual triangles look like, what this is doing is it's summing a triangle that looks like here with the triangle like there, with a triangle like there. And so it's basically 3 different triangles or basis functions that are getting added together. And so when you add them together in terms of the equations, it looks like this. F of x equals a1 b times x minus x1. That's the first one. It's shifted by x1 plus a2 b that's shifted by x2. So that's the third basis function plus a3 times bx minus x3. So the third one is shifted by amount x3. So that's why it's standard right there. Okay, so that's the idea that we're going for. We got these basis functions, and they're going to get added together so that you end up with a piecewise linear function that looks like this. Let's look at how we represent this in matrix form. So in matrix form, the overall pattern is the same as what we've had before. We had a Y matrix, a Z matrix, and an A matrix, and the Z is n by n, the Y is n by 1, and the A is n by 1. And then in the middle of the Z matrix, instead of being a columns of ones and then squares, they're combinations of these basis functions that are shifted by different amounts. For a linear B-spline, so basically, this is what it shows for in general for B-splines that may be of different shapes, but the B-splines that we've talked about so far are very kind of like simpler shaped. And so for these, at B at 0 equals 1, and also B at x greater than h equals 0. This is just saying that the width of the B-spline is no more than h, as we saw. And when both of these happen, then the Z matrix, basically what happens is that the B0 being at 1 means that the center diagonal is all 1s, and the width of the basis functions being no more than h means that all these off-diagonal terms go to 0. And when we do that, Z simplifies down just to the identity matrix. And so if Z is just the identity matrix, then identity times A is just A. So then which means A is given by Y. Okay. And then once you solve for these coefficient matrices, then for new values of X, this is sort of like what it was like for the polynomial interpolation, where it's going to be a sum of the y's multiplied by the basis function. So basically, you're going to be plugging in new values of x that you want and running it through this equation. So what we've been talking about so far are linear B-splines that were pyramid shaped, but it's also important to know that there are other types of splines that are more rounded, like these. So this is what's called a cubic B-spline. And the nice thing about a cubic B-spline, as it shows at the bottom, is that it makes rather smooth interpolating functions. It kind of goes very smoothly through the data points. Whereas when we looked at the linear B-splines, it's a very sort of a piecewise linear type behavior, which may be a good thing or a bad thing depending on how you're using it. Okay, so finally, let's look at an example of using these B-splines. So B, or B of X, equals the max of 1 minus, and then in this case, our step size is 2. because we're looking at using data at 1, 3, and 5, and so our step size is 2. Okay, and that means that the basis functions that we're dealing with look like this. Okay, and since we know from the B-spline slide a couple just a bit ago that the A matrix we give is exactly the same as the Y matrix. So A is very simply it's the 3 values. So we're taking data at 1, 3, and 5, which is 0, 1.099, and 1.609. 0, 1.099, okay? And then, so that's the solution to the coefficients is given almost right away. And then we're going to plug this in to find a function that uses these B-splines to connect the data points together. And so that's given by 0 times b to the x minus 1 plus 1.099 times b to the x minus 3 plus 1.609 b to the x minus 5. Okay. And now when we want to, so this is a general equation that would be the interpolation for any new value of x. And specifically when we want to solve for x equals 2, we would plug in x equals 2. So obviously this first term is already 0. The second term is 1.099 times max of 1 minus. And notice that because this is x to minus 3, so up here is 2 minus 3, because 2 is the value of x, and 3 is the shift of this basis function, divided by 2. And then the third basis function here is 1.609, but we know that after 2 it goes to 0, and x minus 5 is definitely all the way at past that, and so that's all going to be 0. And so if we calculate what's left here, we've got 0.5 times 1.099, which is 0.4 or 5495. And so note that this is actually the same result as we had before, because this just happened to be a value of 0 at x equals 1. All right, so this is the answer for this problem. So let me then quick show you graphically what's happening here on this plot, is that the x at x equals 1 value is there. At 3, it would have it and be like this. And then at 5, it looked like this. And so the sum of these is given by this orange line. It should be 0 like this, and then come down. Okay, so this last concept is extrapolation, And the main point here is you need to be really careful when you interpolate because you can be misled. So, for example, say we've got a real function that does something like this. But if you were only linearly using linear interpolation, you might think that from these 2 points, if you had these 2 points that you're interpolating on, it would look fine like in the region where you were interpolating, where you already had data, but beyond this place where you had data, you can get very far from the real function. And you could also get quite far from the real function if you had a quadratic. Let me show you a quadratic now. If you were using all 3 of these, remember that the interpolation would look good it's not the best quadratic, but the interpolation would look good while you're within the data points that you're interpolating. But when you're going beyond those data points, that quadratic is likely to diverge very far from the solution. So the overall lesson here is extrapolation is really prone to error. So in this section, we've looked at how interpolation allows estimates of intermediate values between known data points, that interpolation error decreases as the step size decreases because it gets easier and easier to interpolate, that higher order polynomials, that while they can still make sure that it goes through the data points, they can also lead to high errors, especially when you're extrapolating. And finally, that B-spline interpolation approximates the error using a sum of simple basis functions and gives piecewise linear interpolations of your function. So thanks. Hope that was useful for you, and see you next time.